Dear students, welcome to 22nd online class of Control System Engineering. We are studying the topic of root locus, which give us graphical representation of closed loop system poles when unknown parameter of the system is varied. In last class we studied rules related to sketching of root locus. First rule is the number of branches of root locus equals the number of closed loop system poles. Second one, the root locus is symmetrical about the real axis. Third one, on real axis, the root locus exists to left of an odd number of finite or infinite open loop system poles or zeros. Fourth one was the root locus will begin at the finite or infinite poles of open loop system and will end on finite or infinite zeros of open loop system. Fifth rule defines the path through which poles will reach to the location of open loop system zeros which are at infinity with the help of asymptotes. And the sixth rule we studied was j omega crossing. J omega crossing give us the frequency of oscillation, and it also separates left half plane from the right half plane. Dear students, after this lecture you will complete the sketching of root locus. Dear students, contents of this lecture are the remaining rules of sketching the root locus, which are break-in or breakaway points, angle of arrival or angle of departure, and summary of the rules used in sketching of root locus. Dear students, now we will study break-in or breakaway point on real axis. Various root locus appear to break away from the real axis as the system poles move from real axis to complex plane. And sometimes locus appear to return the real axis as a pair of complex poles and then become the real poles. If you look at the figure, in this we have two real poles and two real zeros. Poles are located at location -1 and -2, where zeros are located at +3 and +5. Now if you look at point sigma 1, which is between two poles -1 and -2, at this point the root locus leaves the real axis is called the breakaway point, and the point where the root locus enter the real axis, which is represented by sigma 2, is known as break-in point. Dear students, now we will sketch the root locus for the system given in the figure. This system have two real poles and two real zeros. Poles are located at -1 and -2, where zeros are located at +3 and +5. We will find the number of branches and will maintain the symmetry of the root locus. The real axis will exist between two zeros and the two poles. The poles of open loop system will act as a starting point, where the zeros of the open loop system will act as a ending point. So root locus will start at -1 or -2 and will end on +3 or +5 in S plane. Students, Now if you look at the point sigma 1 on real axis, which is between -1 and -2, is called the breakaway point. And the point on real axis between 3 and 5, where the root locus returns to the real axis, is called the break-in point and is given by sigma 2. At breakaway or break-in point, the branches of the root locus form an angle of 180 divided by n with real axis. And here n is the number of closed loop system poles arriving at or departing from the single break-in or breakaway point on real axis. So for the two poles shown here, the branches at the breakaway point forms. Dear students, if you look at the figure which represents two poles, one at -1 and other at -2, these open loop system poles represent gain k equal to 0. As gain will be increased, so these poles will move toward each other. And when the gain reaches its maximum value on real axis, at that point between -1 and -2, breakaway will occur, and further increasing the gain above that value, the poles of the closed loop system will enter into complex plane. So we conclude that breakaway point occurs at a point of maximum gain on the real axis between the open loop system poles -1 and -2 in this case. Students, the graph of gain is also represented in figure, which shows that at point sigma 1 we have a maximum value of gain for poles at real axis. Dear students, when the complex pair of pole of closed loop system returns to the real axis, the gain will continue to increase to infinity as the closed loop system poles move towards the open loop system zeros. Then it must be true that the gain at the break-in point is the minimum gain found along the real axis between the two zeros. And on further increasing the gain, the poles will move towards the zeros at real axis. This gain k for the closed loop system pole along real axis is represented in figure, and the break-in point is found at the minimum gain in between both zeros located at +3 and +5, and the break-in point is represented by sigma 2, showing minimum gain along the real axis. Dear students, now we will study methods through which we can find breakaway or break-in points. The first method we are going to use is differential calculus. As we know that characteristic equation of a closed loop system is given by 1 plus kg of s into h of s equals 0, or kg of s into h of s will be equal to -1. As we are finding maximum and minimum value of gain k on real axis, so we will find relation of gain k with real axis. For this, k will be equal to -1 over g of s into h of s. Now, the breakaway or break-in points will be on root locus segments. For this, we will replace S by sigma. So K will be equal to minus 1 over G as a function of sigma into H as a function of sigma. This equation then represents the curve of gain versus sigma studied in previous slides. Now, if we differentiate the equation with respect to sigma and set the derivative equal to 0, we can find maxima and minima of gain K on real axis. And those will be our breakaway or break-in points. Dear students, for the system in figure, we will find breakaway or break-in points using the differential calculus. The figure represents open loop system poles and zeros. Now open loop transfer function of this system will be equal to kg of s into h of s and will be equal to k multiplied by s square minus 8s plus 15 divided by s square plus 3s plus 2. Dear students, now we have open loop transfer function of the system. But for all points of the root locus along real axis, we will use the relation kg of s into h of s equal minus 1 and replace s by sigma. So we will obtain our relation in terms of sigma. Now we will solve the relation for value of k and we will obtain k equal minus sigma square plus 3 sigma plus 2 divided by sigma square minus 8 sigma plus 15. Now we will differentiate the relation of gain k with respect to sigma and will set the derivative equal to 0 to find breakaway or break-in point. After solving the differential equal to 0, we obtain sigma 1 equals 1.45 where sigma 2 equals 3.82. Both these points lie on the root locus segment. So these are our breakaway or break-in points respectively. Dear students, the second method we use to find out breakaway or break-in point is known as transition method. This method eliminates the step of taking derivative and making differential equal to 0. Students, the breakaway and break-in point must satisfy the relation sum of 1 over sigma plus zi must be equal to sum of 1 over sigma plus pi, where the system have m zeros and n poles. Here zi and pi are the negative of zeros and pole respectively of g of s and h of s. Students, solving the equation for sigma, the real axis value that minimize or maximize gain k, give us the breakaway or break-in point without differentiating. Dear students, now for the same example, we will find breakaway or break-in point with the help of transition method, that is, without differentiating. Open loop system have 2 zeros and 2 poles, and poles are located at -1 and -2, where zeros are located at 3 and +5. Now substituting the values or location of zeros and poles in the relation of transition method, we obtain 1 over sigma minus 3 plus 1 over sigma minus 5 equal to 1 over sigma plus 1 plus 1 over sigma plus 2. Now simplifying the relation, we obtain 11 sigma square minus 26 sigma minus 61 equal to 0. Now finding the roots or solving the quadratic equation, we obtain sigma equals minus 1.45 and plus 3.82, and both these points lie on the root locus segment on real axis. So these are our breakaway and break-in point respectively, and the result also matches with that of previous example. Dear student, next point in the sketching of root locus is angle of arrival or angle of departure. Now to further refine our sketch of root locus, we will find angle of departure or angle of arrival for complex poles and zeros. The root locus starts at the open loop system poles and will end on open loop system zeros. Now to sketch the root locus more accurately, we will calculate angle of departure from complex poles and angle of arrival for complex zeros. Dear students, in the figure we have pole zero map of a open loop system which have complex poles and complex zeros. And now we will find angle of departure for complex poles. Now for angle of departure, consider a point epsilon on root locus which is close to the complex pole. As epsilon is a point on root locus, so the sum of angles drawn from all the finite poles and zeros to the point will be odd multiple of 180 degrees. We assume that all the angles drawn from all other poles and zeros are directly to the pole that is near to the point epsilon. So the only unknown angle in the sum will be angle drawn from the pole that is epsilon. So we can solve this for unknown angle, which is also the angle of departure for the complex pole. And hence mathematically the relation of angles will be given by sum of angles of zeros minus sum of angles of pole will be equal to odd multiples of 180 degrees. Hence minus theta 1 plus theta 2 plus theta 3 minus theta 4 minus theta 5 plus theta 6 will be equal to odd multiples of 180 degree. Our angle of departure, which is theta 1, will be equal to theta 2 plus theta 3 minus theta 4 minus theta 5 plus theta 6 . Dear students, now we will find angle of arrival for complex zeros. If you look at the figure which have pole zero map of open loop system along with complex poles, this system also have complex zeros. Now for angle of arrival of complex zeros, we will assume a point epsilon on root locus which will be close to a complex zeros and the sum of angle drawn from all the finite poles and all the finite zero to the point will be odd multiple of 180 degrees. Students, here we assume that all the angle drawn from all other poles and zeros are directly to the zero which is near to the epsilon. Thus, the only unknown angle in the sum will be angle of departure drawn from the zero, that is epsilon. So we can solve the relation for the unknown angle and we will get our desired angle of arrival for complex zero. The mathematical form of angles for the given system in the figure will be sum of angle of zeros minus sum of angles of pole will be equal to odd multiples of 180 degree. Or if we solve it for angle of arrival which is theta 2 in this case, will be equal to theta 1 minus theta 3 plus theta 4 plus theta 5 . Dear students, now in the given example we will find angle of departure for complex pole in the system and we will also sketch the root locus. Students, we will start the solution with open loop transfer function which is given by g of s, and g of s is equal to k into s plus 2 divided by s plus 3 into s square plus 2s plus 2s plus 2, which are plotted in the figure in next slide. The system have 1 0 at minus 2, 1 pole at minus 3 and a complex pole at 1 plus minus 1j. Now to calculate angle of departure, we will assume a point epsilon which is close to the complex pole 1 plus j1 in the second quadrant. And it is also assumed that the point epsilon is a part of root locus, so it must fulfill angles criteria. Dear students, we are finding angle of departure for complex pole, and for this we have assumed a point epsilon close to the complex pole 1 plus 1j. Now we will draw the vectors from all the finite poles and zeros of a system to the point epsilon, and we will calculate angle for each vector with the positive extension of real axis. The angle of departure will be theta 1. The angle made up by pole 1 minus j will be theta 2. The angle with 0 at minus 2 will be theta 3, and the angle with pole at minus 3 will be represented by theta 4. Now applying the angle criteria of root locus, which is sum of angle of zeros minus sum of angles of pole will be equal to odd multiples of 180 degree. Here assume k equals 0, then minus theta 1 minus theta 2 plus theta 3 minus theta 4 will be equal to 180 degrees. Now substituting the value of theta 2, theta 3 and theta 4 and solving for theta 1 will give us the result angle of minus 251.6 degree or 108.4 degrees. The sketch of root locus is shown in the figure, where the angle of departure from the complex pole help us to further refine the root locus. Dear students, now we will revise the basic rules used in sketching of root locus. First one is number of branches. The number of branches of the root locus equals the number of closed loop poles. Second rule is symmetry. The root locus will be symmetrical about the real axis. Third is real axis segments. On real axis, for gain k greater than 0, the root locus will exist on the left of an odd number of real axis finite open loop poles and or finite open loop system zeros. Fourth rule is about starting and ending points. The root locus will begin from finite or infinite open loop system poles and will end on finite or infinite open loop system zeros, where open loop system is equal to g of s into h of s, where g of s is forward path transfer function and h of s is transfer function of feedback path. Fifth rule is about behavior at infinity. The root locus approaches straight line as asymptotes as the locus approaches infinity. Further, for sketching asymptotes we require number of asymptotes, which is equal to n minus m, and n is number of finite poles and m is number of finite zeros. Center of asymptote, which is equal to sum of finite poles minus sum of finite zeros divided by number of asymptotes, and angle of asymptotes, which is equal to odd multiples of pi radians divided by number of asymptotes, or odd multiples of 180 degree divided by number of asymptotes. With number of asymptotes, their origin Dear students, next is real axis breakaway or break-in points. The root locus break away from the real axis at a point where gain is maximum and breaks into the real axis at a point where gain is minimum. Next is calculation of j omega crossing. The point of j omega crossing can be calculated with the help of Routh-Hurwitz criteria. Last point is angle of departure or angle of arrival. The root locus departs from complex open loop system poles and arrives at complex open loop system zeros. And for calculation of this angle, we assume a point epsilon which is close to a complex pole or complex zero. And then we add all the angles drawn from all the open loop system poles and zeros to the point epsilon. And then we use angle criteria, which says that sum of angles must be equal to odd multiples of 180 degree. And the only unknown angle is that drawn from the epsilon, which is close to complex pole or complex zero. Students, solving for the unknown angle give us angle of arrival or angle of departure for complex pole or zero. Now if any of you have any questions, please ask.